So this is lecture number 17 in unit number 3, memory management. So we have already studied about the memory organization in the last class, day before yesterday, and now this is the memory management. So whenever this question arises about the memory management, so we consider memory either it is of CPU or the main memory, that is the RAM, random access memory. Now, how CPU can be shared by a set of processes? Because if there are number of processes are going on, then some of the processes share the CPU and some of processes share the main memory, that is the RAM. Now we can see because with the help of the CPU and the main memory, when it is shared by a number of processes, okay, then how we can improve the system performance with the help of the memory management. And also there is one of the other factors, that is the process management. Okay, if there are number of processes are going on, then first is how we will manage the number of process so that accordingly these process is shared by a CPU or the main memory. Now need to keep several processes in memory. So if there are number of processes are going on, then how we will keep these processes in the memory, or how we are going to share the memory. Either it is a RAM or the CPU memory. Both are used as the temporary memory. Okay, because we are not going to store permanently in both the cases. Either it is the CPU memory or the main memory. So here we also learned various techniques to manage memory. Here how we are going to manage the memory. Okay. Now we can see here the memory, how it is have connectivity with the hardware, or we can say the hardware dependent. So random access memory, whenever we will open our operating our system, okay, then we can say that the RAM is in the hardware form and it is available as the physical memory on the motherboard of the system. So if we are going to manage the memory, then how it is dependent on the hardware. Okay. And here also you can see the CPU memory. This is also the physical memory. Okay. Now here we are not including the concept of the virtual memory. Just we are going to manage only this memory, that is the RAM as well as the CPU. Now here you can see basic memory management. So there are two types of memory management. First is called the basic memory management and another is called the virtual memory. Okay. So basic memory management, it contains logical versus physical address space. Okay. So there is a logical and another is called the physical address space. So logical address space and another is the physical address space. Now, how we are going to provide the protection? What is the contiguous memory allocation, paging, segmentation with paging? So there are several methodologies which we will use during the management of the memory. So how we are going to manage the main memory, then these are the different terms or the factors related to the memory, that is the logical or the physical, how we are going to provide the protection, what is the contiguous memory allocation, what is the paging, segmentation with paging. Okay. Another factor is the virtual memory. Okay. First is the basic memory management, then another is the virtual memory. Virtual memory, what is this? It is not going to exist. Okay, virtual memory. But how we are going to manage different number of processes. Okay, then this concept is called the virtual memory. Okay, how we are going to maintain the different number of processes or the programs in a particular provided memory. That is, if we have the fixed RAM, random access memory, or the main memory, then how we are going to manage our programs or the procedures, or we can say the software which we are going to develop, then how your software is going to process within the available main memory, then we can say we will use the virtual memory concept. So what is this virtual memory concept? We will study about this also. So what is the background of this, of the virtual memory? What is the demand paging? So these are the terms related to the virtual memory. That is the background. What is the background of the virtual memory? What is the demand paging? What is the performance? Okay. What is page replacement? Page replacement algorithm. There are several algorithms which we will use for the replacement of the page, FCFS, LRU. Okay. And allocation of frames, thrashing. So there are number of new words here. Okay. FCFS, LRU. Then we will discuss these terms in next slides. Okay. So what is the background? Background of, here we can see the background of the basic memory and also the virtual memory. Okay. So program must be brought into main memory. Okay. So we have our program into the main memory, that is in the hard disk. Okay. Then as it is going to process, then the operating system will retrieve from the secondary memory into the main memory. Okay. So it will fetch your program from the secondary memory into the main memory, that is into the RAM, random access memory. Okay. Because ultimately, finally, it settled down on the secondary memory, that is on the disk. Okay. So program must be brought always from secondary to main, that is from the disk into the main memory. Okay. So fetch, decode, execute cycle. So here we use this. We fetch the program and then decode and then execute cycle. Now in this block diagram, you can see here central processing unit, how it is connected with this RAM, random access memory. Now, as you are going to execute your process, so first it will, to execute, it will come in the central processing unit. Okay. So after processing, it will go to the, again to the RAM. Okay. And then it may go to the other side. So from the RAM, we can also retrieve our program from the RAM, and it will go to again to the central processing unit. Here we can see only the one part. Here the access on both sides, vice versa. Okay, the data will go from CPU to RAM or from RAM to CPU. So here just it is the one cycle. Okay, so fetch, decode, execute. Just so we will fetch from the secondary storage here, and then decode and then execute. So execution will take place in the central processing unit. Okay, so this is the temporary here. The RAM holds the data temporarily. Okay, and again it will go to other side. Now here we can see memory unit only sees a stream of addresses. So in the memory, we just find the address, or we can say if there are a number of processes, then we can say the stream of addresses. We have a number of addresses here. Okay, plus read request. So we also have the request. Okay, address plus data. So here we may also have the address as well as the data and the write request. So we receive several requests, read request, write request, or the address and data, or address plus read request. Okay, so anything uh, could be happen in the memory unit. Okay, so sequence of memory addresses. Now here we can see sequence of memory addresses generated by the running program. So whenever we will run our program, then it will generate a sequence of memory address. So we will get some sort of address here. Now, what is the difference between the logical versus here we can say physical address space? Okay, what is the difference between these two? Now you can see logical address means generated by the CPU. Okay, so whenever your process will go in the CPU, then CPU will generate a address. Okay, so that is called the logical address. So also referred to as virtual address. So sometimes it is also called the this virtual address. Okay, so it is generated by the central processing unit. Then it is called the logical address. Okay, and sometimes it is also called the virtual address. And what is the physical address? Address seen by the memory unit. Okay, so MMU, this is the memory unit. Here we can say main memory unit. Here, so address seen by the memory unit. Just we are indicating by the MMU. Here, then this is called the physical address. Okay, so we have the physical address as well as the logical address. So logical address means generated by the CPU, and what are our address we will see here in the memory unit, then this is called the physical address. So logical address space, what is this? Set of all logical addresses generated by a program. Okay, so whenever we will run the program, then we will get a set of logical addresses, that is called the logical address space. And physical address space, set of all physical addresses generated by a program. So this is the physical address generated by the program, and this is the logical address generated by a program. Okay, so the program generates two type of address. First is called the logical address, and another is called the physical address. So physical address we can see in the memory unit MMU, and logical address in the CPU, that is generated by the CPU. So this is the difference between the logical and the physical address. Now in the diagram you can see here, this is the one of the diagram. Here CPU, central processing unit, logical address. So we will get suppose here 346. So this is the address which is generated by this, that is the central processing unit. As the program will come here for the execution, then during the execution of the program inside the central processing unit, it will create a logical address, and that may be in the form of the hexadecimal code or some other codes. Okay, so just we are getting this logical address. Now this is the memory unit. Okay, so relocation register, here we have some register to hold the data. Okay, to store the data temporarily, and this is the address for this particular register. Okay, so each and every register have its own address here. So this is 14000, you can see here. So this is the address of this register. Okay, so whenever the process will come and store here, then this will be the address for that particular here program. Okay, then we can say this is the address for that particular, where we can say procedure or the function or the program, and this block diagram is indicating the memory unit. Okay, so as the logical address will come here, okay, and here we are going to store, again it is changing. Now this is the original address of this. Again now you can see here, this is the physical address, again it is changing 14346. Yes, you can see here 346 is the logical address, and this is the address of the register. And now what will be the physical address here? Then you can add this 346 14000, then 14346. This is the physical address. Okay, so logical address plus address of the relocation register. That is, we can see inside the memory unit, and then we can get the equivalent address here, that is called the physical address. Okay, and now it will go to the here memory. So this is here the memory unit, and now it will go to the memory. So here we can store it permanently in this. Now this is again, you can see the background. If there are multiple processes resides in the memory, so whenever we will consider here the discussion, then it must be related to the RAM, random access memory. Okay, so here you can see this is the uh, block diagram for the random access memory here. So multiple processes resides in memory. Okay, so protection of memory required to ensure correct operation. Now always at the upper layer here you can see in the operating system will reside here. Okay, so we can say here process 1, process 2, process 3, and this is the unused area. Okay, still we have uh, some more area, and here we can store other processes. Okay, so this is the free space. Now this is the address here, just it is going to mark 0, and this is the we are going to divide into several parts here. So 2, 5, 6. Now again here you can see, so this is the nomenclature or division of the address. Maybe in the hexadecimal form we can write, or some other code we can use. Okay, so how we are going to provide the protection of memory required to ensure correct operation. Now here we can see there are several processes are running. Okay, and this is the base, now base address here, and this is the register. Here we can see again it has some location or the address. Okay, so protect OS means protection of the operating system, protect user processes. So protect operating system, just we have the operating system, it will lie on the upper layer of the RAM, random access memory, whenever we will boot our system. Okay, so then from the secondary storage, it will come to the upper part of the random access memory. So this is the upper layer, and after that, this area is reserved for a number of processes. Okay, which are going to run or which are executing. Okay, then we can say how we are going to provide protection to the operating system. So this is the protected area and reserved for the operating system. Okay, here always the operating system will reside in the main memory. And how we are going to protect our different processes, then here we are going to divide into a number of addresses, and this particular area is reserved for process, and this is again new process, and again this is new process, and it has some base address and also some register address here. Now we can see what is the base and the limit registers. So there are two types of here registers, base and the limit registers. So this is the address for the limit and base registers. Here you can see this and this. Now a pair of base and limit registers define the logical address. Okay, so on the behalf of the base and the limit register, we can define the logical address. How we are going to get the logical address space? Then just we will consider there is a pair of both registers, that is a base and a limit. It will give you the logical address space. Okay, so now we can see this is the division of the area here to store the several processes, process 1, and this is fixed one. Okay, and it will depend on the length of the process. Okay, we are going to use, so this is not fixed here, address is not fixed here, but it will depend on the allocation of this particular process, how much area is covered by this or occupied by this process and this process. So accordingly, we can divide the address space. Okay. So these are the two different registers here. We are using base and limit registers. So with the help of this, we can define the logical address. Now hardware address protection with base and limit register. So how we are going to provide the protection here. So now you can see. So this is the CPU, central processing unit. So it will give you some address. Okay. So it will generate the logical address. Okay. CPU always generate the logical address. Now here you can see this is the base register. Okay, it is going to store in this. So is address greater equal to, if the condition is true, then it will go there here. Okay, it will add the both base plus limit register space. Otherwise, here no trap to operating system monitor addressing error. So here we will get some sort of error. Okay, if this is not true or false, or if it is okay, then it will proceed, and then we are going to add both register. The operating system will add both the address of base and the limit, and here we will get the logical address main. Yes, if it is okay again. If no, then again we will get some sort of error here, or otherwise if it is fulfilling all the condition, then if it is okay, then we will get the address in the form of the addition of the address of base and limit. So here we will get the address. Okay, actual address, real address. So operating system loads the base and limit registers. So your program will go in the base and limit register. Okay. So privileged instruction. So there is some, we have some rights. Okay. So whenever the operating system loads base and limit register, then we will get here the complete logical address here. So it has the connectivity with this memory again. After the CPU, we will proceed towards this memory. Now address binding, what is this? Process resides in main memory. So address binding, where we will get the exact or the complete address, then process resides in the main memory. Associate each data element with memory address. Further addresses represented in different ways at different stages of a program's life. So there is a source code addresses, usually symbolic. So we use some mnemonics for this of the source code. Compiled code addresses bind to relocatable addresses. Okay, so whenever we will get this address, complete address, then the we are going to bind with the compiled code addresses. So we have the different addresses, and after that we will add both addresses and we will get the final address, that is called the relocatable addresses. So 14 bytes from beginning of this module. Linker or loader will bind relocatable addresses to absolute addresses. So similarly, in this case, if the program is running, that is the compiled code addresses bind to relocatable addresses. Similarly, in case of the linker and loader, again will bind relocatable addresses to absolute addresses, and we will get the final address here. So this is called the address binding. Now here you can see multi-step processing of a user program. Now the program will start from here. This is the source program, the program written by the user. So this is the source program, and this is in the high level language. So it will go to the compiler or the assembler. Okay, so here we can use either the compiler or assembler. If we are using the compiler, then it will give you the compile time. Assembler, then again we will get the some time, but here the code will be different. Okay, here we will use the assembly language, but in case of the compiler we will use the high level language here, and it will convert to the high level to machine language, and in case of the assembler it will convert assembly language to machine language. Okay, so here we will calculate the compile time, and after that from this part we will get the object module. Okay, either we can use the compiler or the assembler. Then here we will get the object module. After that you can see, if we have other object module, then with the help of object module and other object module, we are going to combine. Here we will get the linkage editor, how it is going to provide the linkage with both of these two modules, how we are going to link both these modules. Then for that we will use the linkage editor. Okay, so we here we can combine or we can link other modules. Now here we will get the load module. Okay, so these are the various parts here. All these parts are inbuilt with the operating system. Then load module here. Here we have the system library. Then this is the loader. Okay, so the loader will load your program, the source program into the memory. Okay, so it will load to the here in memory, binary memory image. So sometimes we can get the memory image, or we can say that in main memory. So dynamically loaded system library. So we always have some libraries. Okay, we can use any type of functions here that will be available in the library of that particular system. So dynamic linking, this is called the, and here now you can see this is called the compile time, and here because we are loading our program, so these are the here various we can say the phases. So we will calculate the time. This is called the load time. Okay, so this is called the load time. This is the compile time, and here whenever our program after loading it will come in the main memory, then this is called the execution time. Okay, so in memory, binary memory, here we can say in the CPU. Okay, so we are going to load this in the CPU, and after that it will go to the memory. So this is the execution time. So if the process is executing in the central processing unit, then this is called the execution time or the runtime. So there are three times here you can see: compile time, load time, execution time. So these are called the multi-step processing of a user program. How the user program is going to process. So this is the procedure for that. So there is the involvement of the number of steps, that is called the multi-step. How it is going to compile or assemble, or how we will use the linkage editor or loader. Okay, and then it will come to the CPU for the process. Now there are number of binding of instructions and data to memory. So one is called the here compile time. You are already aware by this. Load time. Okay. So compile time, if memory location known a priori, absolute code can be generated. So here during the compile time we will get the absolute code. Okay, can be generated. Must recompile code if starting location changes. Sometimes there is a need arise to change the location again. So if we have some error in our program, then we again link and load our program, then the location will change. Okay, so during the compilation, the location address may change. So this is the compile time. Okay, here we will get the absolute code. So absolute code can be generated during the compilation time. Okay, what is the load time? So load time, this will generate relocatable code. Okay, so load time, here we will get the relocatable code if memory location is not known at compile time. So sometimes the if we are not aware by the memory location, okay, then we can generate the relocatable code during the load time. So what is the execution time? With the process can be moved during its execution from one memory segment to another. So there are several segments that is called the memory segment we can use. So during execution of the process, then sometimes it move from one memory segment to another, then it is called the execution time. Then binding delayed until runtime, need hardware support for address. So sometimes there may be delay due to some other we can say problems. Then binding, that is called the binding delayed until runtime. Okay, need hardware support for address maps. So again, it will depend on the hardware support, and hardware support means the base and limit registers. Okay, we always do the base and limit registers, then that is called the need hardware support for address maps. So this is called the binding of instruction and data to memory. How the data is moving from one segment to another segment. That is also called the compile time, load time, execution time. So there are three times we will use. Now here you can see logical versus physical address space. So you have already seen what is the logical address generated by the CPU, or sometimes it is also called the virtual physical address seen by the memory unit. Okay, so it has the interface, CPU has the interface with the RAM, random access memory. Now you can see here logical and physical address are the same in compile time and load time address binding scheme. So logical and physical address here remains same during compile time and load time, and after it may change. Now what is the logical? Logical, it is also called the virtual. Okay, and physical address differ in execution time. So both logical and physical address, it will differ in execution time address binding scheme. So the address, physical address and logical address will be different. Okay, here we can say logical address space. We have already seen set of all logical addresses generated by the program. Similarly, physical address generated by a again program. So both are the space generated by the program. Okay, and logical address, it is generated by the CPU. So what is the MMU? This is called the memory management unit. Okay, sometimes it is also called the memory unit. Okay, so memory management unit. This is the MMU. So hardware device that at runtime maps virtual to physical address. Okay, so virtual address to physical address. If it is connected with the hardware device, then we can say at runtime it maps virtual to the physical address. So at the starting we have the logical address, and then it is converted to the physical address. And your process will go to the where, to the memory. Okay, so at it instant, at the same instant it will go to the MMU, that is the memory unit, then we will get the physical address there. And earlier during the uh, CPU stage, it will generate the logical address. Okay, so there are number of methods we will use for this. Now there is a involvement of the relocation register, and MS-DOS on Intel 8086 use for relocation register. So if we are using this operating system, MS-DOS on Intel 8086, then we have four relocation registers. So these are already fixed and defined there, four relocation registers. Now the user program deals with the logical address. It never sees the real physical address. Okay, just I am skipping this. So no need to go so deep there. Now dynamic relocation using a relocation register. So how the address is changing here, now you can see. So this is the CPU generating logical address, and here the 346, it will come to the here memory unit. Now in the memory unit we have the relocation register. Okay, so this is the address for that relocation register. Again here we will get the physical address. So in preceding slide, we have already seen how we will get obtain the physical address here. Then logical address plus the address of this relocation register. So 14,000, and this we will get the physical address here. So it depend, the physical address will depend on the CPU address. Okay, CPU means it is generated by the CPU, that is called the logical address. Okay, so after addition we will get the physical address, and then here you can see this is the memory here, and this is the relocation register, and this is the address for that 14,000 here, and here we will get the relocatable code. So it will generate the relocatable code inside this memory. Okay. Now, what is the contiguous allocation? What is the contiguous memory? So multiple processes resides in memory. You can see here. So this occupied area. Okay. So this is the unused area. This is the first area occupied by your process one, and this is process two and process three. Okay. So we have the limit, this address, and again the base register address. So there are two types of register we'll use here: limit register and base register for each process. Okay. So this we can define here minimum and maximum address space here. So this is the address occupied by this process. So because there are multiple processes resides in memory, then this memory will be divided into several addresses here. You can see. So this is the process how each process will occupy the area. Then this area is called the contiguous allocation. Okay, but in case of the contiguous allocation, sometimes we again have some free space. Okay, suppose this is process one, but this is the part of the memory occupied by the process. So it is not definite that the whole area of this main memory occupied by this process. So there are some space left, okay, in this memory. Then this is that is called the contiguous allocation. Okay, so sometimes some space left here. Contiguous means process one, process two, process three. Yani ki after this space, we are going, the another process is going to allocate the another new area. Okay, and this is again the new area which is allocated by this process. Now there are we can say some memory spaces left. Okay, then we can say that this is called the contiguous memory allocation. Now here you can see contiguous allocation. Main memory usually divided into two partitions. Just we are going to divide into two parts. This is the main memory, means the RAM, random access memory. So resident operating system. So in the upper layer, you can you have already seen that resident operating system means operating system will reside here, usually held in low memory. Okay, so there's a fixed memory here, or we can say that is only few. We can say only the limited portion which is occupied by the operating system, and rest of the memory will be used by a number of processes, and it also have some free space still. So user processes then held in high memory. Okay, each process contained in single contiguous section of memory, means this is the fixed one. Okay, and this is the fixed memory. We can say the area that is occupied by a particular process. So single contiguous section of memory means the fixed memory, okay, of the RAM, random access memory. So it is not necessary this area uh, will be equivalent to the area occupied by a particular process, maybe some more or less. Okay, and I will tell you regarding the contiguous or non-contiguous memory allocation in some other slides. Okay, so each process will occupy the single contiguous section of memory. Now just I am taking your so again we can see here contiguous allocation, multiple partition allocation, how we are going to divide this allocation memory into number of multiple parts here. Divide memory into several fixed size. Okay, so we can divide either in the fixed size or some we can say non-fixed, that is floating. Okay, so the parts may be equal or not. It will depend on the procedure or the method we are adopting. So each partition stores one process. Okay, so we will divide the random access memory, and here each partition stores one process only. Okay, degree of multi-programming limited by number of partitions. So if we are using the multi-programming here process or the method, or there are a number of programs which are running, then means limited by a number of partitions. So it will occupy in more number of parts. If a partition is free, okay, load process from job queue. So we have the job queue, there a number of jobs will wait, and then it will load to the that particular partition which is free. Okay, so we can see in this IBM OS 360, we are going to consider the one of the example for that. Okay, so this is we can utilize this